Lesson 9-6, solving rational equations. So you guys have been working with rational equations, so this module 9, you guys can multiply, divide, add, subtract, look for direct and inverse relationships. And now we're going to be setting up some equations and solve them. So let's jump into the book examples. Of course, like normal, I'll do all the book examples and then pick some from the main questions. Example 1. So copy down what they got here. They have 7/12. And I'm going to leave a little space here so I can get a common denominator. So plus, and then 9/x-4. And this whole thing is equal to, another little space here, 55/48. All right, so there's a, right, well, what could be the common denominator? And you see that 12 goes evenly into 48. So I think you do 12 times 4. Here, let's do that. Let's do 12. I need a 4 down here because 12 times 4 would be 48. Okay, so now that looks like that. But okay, I also need this x minus 4 bit. So let's also multiply x minus 4, x minus 4. Remember the theory of what we're doing, where like this bit right here is equal to 1. This bit right here is equal to 1. So we're just multiplying by 1 just to get this common denominator. All right, so same thing here. This middle fraction needs 48/48. And this last one needs x minus 4/x minus 4. Okay? Now, all these terms. We got a term there, and I got a plus right here. That's plus. Okay. This term right here equals this term right here. They all have the same denominator because there's 48x minus 4, 48x minus 4, 48x minus 4. It's all the same. Okay. So here, go ahead and distribute this on top. 7 and 4 is 28. We're going to distribute that 28 into the x to the negative 4. 9 times 48, I can multiply that. And then this 55 is going to distribute here. All right, so let's see what this looks like. Got 28x minus, I think it's 112. Right. Now this is all over. Okay, I have a common denominator here now, 48 and x minus 4. Okay, okay, and then plus, now 9 times 48 is 432. Okay, this is all equal to, that's 55x minus 220, that's right, over 48, and then x minus 4. Okay, there's different ways you could finish this off. Right. What I might do is this. Here, if this fraction is equal to this fraction and they have the same denominator as each other, doesn't that mean that their numerators have to be equal? Okay, I'm going to go ahead and do that. Right. Again, different simplifies. Now, by starting this denominator, I do want to keep in the back of my mind, I know that x cannot be 4. So if I do all this blah, 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 and I somehow get x equals 4 at the end, I got to remember that you can't divide by 0. So I have to not consider that. I would consider that extraneous. But let's see. So we'll just simplify to this. 28x. Oh, here, I can put these two together. What's 432 minus 112? Okay, that's 320. So plus 320, that's equal to 55x minus 220. Okay, well, let's get all the x's on one side and get the constants on the other. And so I'll subtract over 28x minus 28x over here, and I'll add the 220 over. Okay, that looks like, is that 540, I think, equals, what's 55 minus 28 is 27. That's x. Okay. All right. Since we're solving for x, divide both sides by 27. So 7 right there. So, all right. So what's 540 on 27? That is 20. Wait. So x is equal to 20. Okay. That looks reasonably true. Right. If you really want to check, you could take this answer, plug it back to the original statement, see if it's true. Also, remember, double check, make sure you're not accidentally dividing by 0 anywhere, which is not the case, because if I got 4, that would be a problem, but 20, that's fine. All right, so that's one example down. All right, so that's about it. All right, rational fractions, get common denominator, all right, the whole thing. All right, just like we've been doing the last 2 weeks. All right, example 2, solve a rational equation with an extraneous solution. Ooh, extraneous, ooh, right? So, hey, that sounds like what I was worried about before. Okay, well, I know I can't divide by 0, so I got to throw up x equals 4 if that were the case. Okay, let's go. So, example 2. You know what? This one's kind of big, and I'm going to move this book out of the way, so I'm just going to copy it from off screen. Okay. All right. Yeah, it makes it easier to write like this. Okay, I got 2m over n minus 4. Okay. Now I'm going to, again, leave a space here for possible common denominator. Okay. All right. Then I got this fraction. It goes m squared plus 7m plus 4. Okay. Now I was thinking, could I factor that? But I don't think that's easily factorable. Okay? But I think this denominator might be. It's 3m squared minus 18m plus 24. Okay? One thing that stands out to me right away is that all three terms of the denominator are multiples of 3. So I could definitely pull a 3 out. And after that, I can probably factor it. Okay? And this is all equal to, I got a 4m over 3m minus 6. Right? Ooh, also multiples of 3. So I could pull a 3 out of that too. Ooh, I bet I have to have a 3 as part of my common denominator. Sure. And so for now, this 2m over n minus 4, I'm just going to leave alone. Okay. Let's check this middle term here. All right, so the m squared plus 7m plus 14, just leave that right there. Okay. I'm going to pull 3 out here, and then that would be m squared minus 6m plus 8. That's what that's going to be. Then over here, pull a 3 out here, I got n minus 2. Right. Right now, but what I really ideally like is if I have an n minus 4 here and n minus 2 here, I wonder if this will factor out. Oh, hey, that is how that's going to factor. Okay, that's great. That's the best possible way this could have gone. Of course, it's a book example. That's why I'm looking for. Did they set up something that would be easy to solve? Yeah, I think they did. M squared plus 7m plus 14. Okay, got 3. Okay. Here's how this is going to factor. I got m minus 2, m minus 4. Because watch this FOIL. M squared, ding. Negative 4 and negative 2m, ding. 8, ding. It's all there. It's all there. Okay, equals 4m over 3 m minus 2. Okay, now I got some bits that definitely look the same. Okay, so actually, I think this denominator right in the middle will be the common denominator. It's got the m minus 2 like this guy does. It's got the m minus 4 like this guy does. It has a 3 like this guy does. Okay, but this first fraction needs a 3 down here, so I'm going to multiply by 3 over 3. And this bit's equal to 1. That's why it's going to be okay. And also needs the n minus 2. Well, actually, maybe I can put that in front. N minus 2, n minus 2. I'll squeeze in right there. Okay, I'll be right. Okay. And then this last term on the right side needs the n minus 4. So I need an n minus 4 down here. So to balance the equation, of course, I'll also put it on top, restore balance. Okay. So now this looks like this. Okay. Okay. Now, if you look carefully, m, the 2m times 3 is 6m. So this right here is 6m. I'm going to distribute that to both of these parts. That gives me 6m squared minus 12m. Okay. These are all about to be over the same denominator, so I may as well take care of that. 3m minus 2, m minus 4, okay, equals, and then same thing, 3m minus 2, m minus 4. Okay. And so I got minus this m squared. Now this negative is going to distribute, so I'll say minus 7m minus 14. Okay. And then over here, distribute this 4m. I get 4m squared minus 16m. Looks like that. Okay. I'm going to do the same trick I did with the last question, which is this fraction equals this fraction. The denominator is the same. So therefore, the numerators must also be the same. Okay. Now, as I strike this out, remember, in the back of my mind, I know m cannot equal 2, and also m cannot equal 4, because if those were the case, then I would be dividing by 0. Okay, so in case I happen to get that as the final answer, I know that would be extraneous, which is probably where they're going with this. If you graph that, it would show up as a whole if that was the case. And so let's keep going then. So now the numerators. Well, 6m squared minus m squared is like 5m squared. This is negative 19m. And then minus 14 equals, got 4m squared minus 16m. Okay, let's get this all set to 0 and see if we can factor it. It's like something like that. So minus 4m squared on both sides and plus 16m on both sides. Okay, so it's going to be just regular m squared minus 3m minus 14. Is that right? Equals 0. Okay, is that 5m squared? Let's see. Yeah. All right. I see I made a mistake. I can fix this though. Let me go way back, way back. I made a mistake. This 14 is not 14. I go way back to the beginning. All it was 4. Now somehow when I went from here to here, that turned 14. So I'm going to correct myself here. Call this 4. That means this is 4. It's just going to carry down. This negative distributes to still 4. It's just -4 now. Okay. So this is -4. And this is -4. Okay. So I just corrected myself. It wasn't 14. It was 4. Okay. Now this should be factorable. Okay. I got something was there. Okay. M. Okay. That would be what I think it's +1 and -4. So that's going to go. Okay. Because here, let's do a FOIL check. M squared. Bing. And -4 M&M's that bing. 1 times -4 is -4. Bing. Yeah, it all checks out. So I'm getting M equals -1 and M equals +4 because -1 this would 0 out, +4 this would 0 out. Okay. But one last little detail. Remember, I actually had crossed out the denominator before. So I said, as I was doing this, I was saying, remember, M cannot be 2 or 4. Well, here I'm saying M is 4, but then back in the original statement, I would be dividing by 0. So now there's only one answer. And that's M is -1. This M is 4 is called extraneous solution. And that would be, that would show up as a hole on a graph if you said like y equals and graph this whole thing. All right, so it's all right. All right, example 3, mixture problem, mixture. Okay. So rubbing alcohol, commonly used as an antiseptic, contains 70% isopropyl alcohol. Suppose you're adding 50% isopropyl alcohol liquid to 200 milliliters of a liquid that's 91%. Right? How much of the 50% should be added so that you achieve the 70%? Right. So here, going to draw what they just said. Right. They said you have 91% 91% isopropyl alcohol. In fact, you have a set amount of that, which is 200 milliliters. Okay. You're gonna pour this into, or we're gonna make a container here. Okay. Okay. So let's say I'm pouring this in for that. Okay. Then you have this 50% isopropyl alcohol, and the amount there we'll call X. And that's the question: how much X should you put in? Okay. So when we mix this all together, we end up with 70% isopropyl alcohol, right? And they didn't specify how much volume, but it's going to be more than 200 milliliters because 200 from here, something from here mixes. Okay? Now, before I go setting up equations and plugging and chugging, right? You can almost see the answer. Because what if I change this 91% by a tiny, tiny bit? What if I make this 90 exactly? Okay, so if this is 90%, and I do 90%, 50%, the average of that is 70%, which is what we're targeting. So it's really close to half and half. Now, the fact that you tweak this a little bit, make this 91%, well, this is going to be a tiny bit more than 200 milliliters is what it would be. So how can we create an equation that describes the situation? So I'm going to go 91% times 200 milliliters plus 50% times X milliliters results in 70% times, well, it would have to be X plus 200, wouldn't it? X plus 200, that'd be milliliters right there. Okay, so that's the equation that you want to figure out how to come up with from scratch, and then the rest of the steps is going to be algebra. Okay, so to go over this again, 91% times the 200 milliliters, right? There's like some amount of alcohol, you think of it that way. Okay, and we've got 50% times something that we want to solve for. How much volume? That's the question. Okay, we pour this all together, and it's going to average out to 70%. Okay, and the volume, so 70% of what? Of the volume, which is whatever we poured into X plus the 200 from here. Okay, so that's going to be the equation. Okay, solve for X, which shows up in 2 places. Okay, now a few ways to finish this off. I'm going to strike the milliliters and just go with the numbers. Okay, the percentage you could change to 0.91, 0.50, 0.70 as decimal values, or just leave the numbers. I think it really matters. Okay, because we'll get the same X value anyway. Okay, so yeah, maybe I just leave it. Let's do that. Let's do 91 times 200. Okay, so I'm getting 18,200 here plus 50x, I'll call it here. And then equals 70x plus 7 times 2 is 14, and there's 3 zeros. So we'll get that. Okay. Yeah, now we can solve for x. Shows up in there. So subtract off 50x minus 50x. And over here, I'll subtract off 14,000 minus 14,000. Okay, see what this looks like. So this would be 4,200 equals 20x. So 4200 over 20. Yeah, that's like right in line with about what I thought it was going to be. The unit is milliliters. Okay, remember how I said, okay, if this was 90 and 50, it would be exactly a 50-50 mix. So you need 200 and 200. Okay, but this strong one's a little stronger than that. So you do need a little more volume on the more dilute one. Okay, and it is. It's a little over 200 milliliters. It sure is. It sure is. That makes sense. Okay. All right. Distance problem. Mexican free-tailed bats have an average flight speed of 25 miles per hour. It takes one of the bats 5 hours to fly 121.8 miles round trip one night. I assume that's actually the total distance. Yeah. Assume that the bat flew at a constant speed. Determine the speed of the wind. Okay, so it's probably like fighting the wind one way and then getting a boost from the wind the other way. Okay, so something like that. So here, draw this out. Example 4. Okay. You got this bat. Okay. Or bat looks like probably something like that. I got a little bat here. All right, this bat's gonna take a trip. Say to wherever, maybe to this tree over here, and then also go back. So it's there and back. Okay. Um, okay. And the speed of the bat, call it v bat in physics, we use v for speed, it's like velocity. Okay. So is 25 miles per hour. Okay. So we'll do everything in miles and hours, and yeah, the unit should all work out. Okay. So it says round trip of 121.8 miles. I'm going to divide that by 2. 121.8 divided by 2. Okay. Because it assumes maybe equidistant there and back. So this distance is 60.9 miles. Okay, so 60.9 there, 69.9, do it back. Okay, so that round trip therefore is 121.8 miles. Okay, so we got that. Okay. And also the time for the round trip, so t for time, is 5 hours. Okay. Now there's wind. Now maybe the wind is blowing to right or to left, but it's symmetrical, so mathematically it doesn't matter which way. Okay. Let's have the wind blowing. How about uh, how about to the left? Okay, right. Okay, I'll call that v wind, the speed of the wind. Okay, and that's the question: is what's the speed of the wind? Okay, because watch this. If I get rid of the wind, I can guarantee it's going to take less than 5 hours to make this round trip. Okay, because you guys know distance equals speed times time. Speed times time. Okay, the physics way of writing this could be like x equals dt, something like that. Same idea. Okay, so if you went 25 miles an hour here, and you have a total round trip of 121, watch it, 121.8 miles total. If I divide that by 25 miles per hour, see, it only takes 4.87 hours if there is no wind at all. Okay? Once you throw wind in the mix, the bat's fighting the wind one way. Now it is getting boosted the other way. So you might say, well, wouldn't that be a wash? Right? But it actually spends more time fighting the wind because it's going so slow. Right? And it spends not very much time with the wind because the wind gets it back really fast. Okay? So the wind will always overall slow down. If you're doing a round trip, if you're fighting it one way and getting boosted the other way, overall you slow down. So instead of taking 4.87 hours, it takes 5 hours. Right? But what is that wind speed? Okay, so how can we set up an equation or a system of equations? Okay? Well, I can actually play off this, and I can say we actually have two different speeds relative to the ground. This is the bat relative to the surrounding air. Okay? The wind is the air relative to the ground. Okay? So we can do a trip there and a trip back and make a couple of equations that way. And a one-way trip is only 60.9 miles. So say 60.9 is equal to now, it looks like he's fighting the wind one way. Let's do fighting first. So fighting the wind would be 25 miles per hour minus the wind speed. Actually, here, I'm just going to call it W for wind speed. Let's call this W. That's easier to write. Okay. And well, some amount of time. So I'll say time A. Let's say the time A is there and time B is back. Okay? Because we don't actually know that yet. Okay? Now he does make the same distance back. It's still 60.9 miles back. Okay? Now he's getting a boost from the wind. So it's 25 miles per hour plus the wind. Okay? And that's time B. Okay, so that's another equation. Okay? Now the third equation we know is we know what time A and time B add up to. They add up to 5 hours exactly. So I'll say 5 as in 5 hours is time A plus time B. Right? And this right here is our system of equations. Okay? Now, you do enough of these, what you realize is that if you have a number of independent equations and a number of unknown variables, then if those match, you can solve it. So what do we not know? We don't know the wind speed, which shows up there and there. That's one variable. We don't know time A, which shows up there and there. That's two variables. We don't know time B, which shows up there and there. And that's three variables. And so we have three unknown variables. I'll say three unknowns. Okay. But also three equations. What that means is that this is solvable with what we have. So we have enough equations to be able to solve this. Yeah, so let's do that. Okay, now how can we do that? I think probably a series of substitutions. Let's try this. Okay. Like I can get one of these times in terms of the other and substitute it into one of these. Right? And then now narrow it down to 2 and 2, like two equations, two unknowns. Right? Well, I can set these equations to each other because they're both the same distance. Right? Okay, yeah, I see it's all coming together. Okay, can you guys see forest for the trees, see the big roadmap? Let's go for that. Let's do exactly what I just said. And so maybe I'll find time B equals 5 minus time A. That would also all be in hours. I just took this one and rearranged it. Okay. Then let's substitute that up here. Okay. And also set B's equal to each other because they're the same distance. Okay. So I'll say 25 minus the wind speed. So 25 miles per hour minus wind speed times time A, which is equal to 60.9 miles, is also equal to this other expression. 25 miles per hour plus the wind speed times time B. But I'm not going to write time B. I'm going to write time B in terms of time A, which is this expression right here, 5 minus time A. Right, here's that. Got some substitutions. Right. Right. Got that. Time B is time A. Okay, well, let's see what happens here on up. Okay. Okay, so I can distribute time A at 25 time A minus W time A equals, okay, that'd be negative 25 time A. Oops, that's that. Oh, sorry, this is FOIL. I have to FOIL this. Oops. Let's FOIL this. It's 25 times 5, it's 125. Okay. Then minus 25 TA, then plus 5W, then minus W time A. All right, keep going with this. Now, I know we have two unknowns at this point in this one equation, but let's play around and see what this does. Like one thing I see is this minus WTA minus WTA. Right, that can cancel. Zip. Okay. All right, then I got this mix. All right, let's do this. Let's add this 25A over here. So plus 20 or plus 25 TA plus 25 TA. Okay, and now what I'm getting is 50 time A on this side is equal to, and then okay, this would zero out. This is 125 plus 5W. Okay. Ooh, we've got multiples of 5 here, so let's pull a 5 out. So that's 10 TA equals 25 plus W. See, I pulled a 5 out of the whole thing, so that's gone. All right, and then okay, now I have a relationship between time A and the wind speed. Well, where else do I have a relationship between time A and the wind speed? Well, that was this equation right here. So I think what I can do is I can make a little substitution here. Okay, so how about this? Let's solve for W and then sub that into that W there. So W equals 10 TA and then minus 25. Right, see, I just took this and rearranged to solve for W, subtract over 25. Okay. Then what I'll do is I'll take this expression right here and I'll plug it into this W right here. And then I'll have everything in terms of time A, and then I can solve for time A. Yeah, let's do that. Okay. So here, just copy this equation. So 60.9 equals 25 minus, right, but instead of W here, I'm going to put this whole expression, 10 TA minus 25. Okay, and then that's all times time A. So put TA right here. Okay, so that's 60.9 equals, right now 25. Oh, well, look at, oh no, it's minus a negative. Oops. All right, so that's 50. And then minus 10 TA. And we got TA. All right, now I do have to distribute. Yeah, this is looking like it's going to be quadratic. All right, so this is negative 10 TA squared plus 50 TA. All right, and then subtract over this, minus 60.9 is equal to 0. All right, well, let's just go quadratic equation. So you got negative b plus or minus the square root of b squared minus 4ac. All right, a lot of negatives flying over the place. Gotta careful about that. All over 2a. Okay, so let's try this. Okay. Now we're getting a plus or minus. So I think that time is allowed to be positive but not negative, just in case something like that happens. So let's go negative 50. Here, I'll pick one of these, and if it doesn't work, we'll do the other. Okay, so let's try plus first. And square root, got 50 squared. Now here I get three negatives, so that's going to consolidate to one negative, 4, 10, 60.9. All right, close the root, close the numerator, divided by negative 20. So I'm getting time equals 2.1, that's hours. Okay. Okay, time A. Okay. Now, had I done a minus here, I would have gotten, okay, or 2.9 hours. Now, interestingly, you guys see how these two times add up to 5 hours? That was one of my conditions. The two times have to add up to 5 hours. So I think actually these represent time A and time B. And what I solved for, I think, is actually the other one is what it is, right? So I'm going to say that time A is, well, if you're fighting the wind, it has to be the longer time. If you're getting a boost from wind, it has to be the shorter time, doesn't it? Okay. So let's go with that. Let's go. Time A must be 2.9 hours, and time B must be 2.1 hours. Okay. But it still doesn't exactly answer the question, which is what's the wind speed? Okay. So wind speed, okay, it has to be one of these. Okay. Actually, we can test this two ways now. Let's do that for the finish. We'll test each of these equations, okay, taking our times right here. So going back to 60.9 equals 25 minus W we're solving for. We're getting close now. Okay, now time A was 2.9 hours. So like that. Well, let me drop the let's call it 2.9. Okay. We'll solve this way. So if I do 60.9, I'm going to divide down the 2.9. That's 21 equals 25 minus W. Therefore, W equals 4. Right? And then that'd be miles per hour is the unit. Okay. So get that. Now, could try the other equation. Let's do the other equation. 60.9 equals 25 plus W, right, when you're getting a boost. Right? But if you're getting a boost, the time is less, so it's only 2.1 hours. So same idea, take the 60.9 divided by 2.1. Okay, so that's 29 equals 25 plus the wind. Okay. Now the wind, again, equals 4, and that's miles per hour. Okay. So yeah, of course, there's one wind speed. It had to be the same either way. Right, that's what we got. Okay. Now, I should say too, right, looking at how your book went through it, your book solved it in such a way it looks like they did not end up using the quadratic equation. So let's just see how they did it. Right? They probably got the same answer though. Right? So they went with distance divided by speed. Okay, that's it. Oh, you could do that too. Distance divided by speed would be the amount of time. Yeah, yeah. So with that, of course, there's two speeds, so you got two fractions. So distance over the one-way speed or distance over the other way speed comes out to the total distance of 5 miles. Okay? They set these fractions, and they were able to you do some cancellation here. You see I'm striking some things, right? Hence, the way they solved it, they got around using the quadratic equation. I used a quadratic equation, right? But okay, you got some blanks here, but I'm sure it's the same thing. It's all good. All right, and we've got one more example, work problem. So let's see here. It takes a 24 row planter, 10 hours to plant a field, and 6 hours if a 16 row planter is also used. Okay, how long would it take to plant the field? Right, if only the 16 row planter was used. All right, so let's figure this out. Okay, now I'm looking at it. Okay, so there's different ways you could go about this, but I'm going to try to save a little time on this video because this goes back to a physics equation right now, and I'll point this out to you guys. Okay, so this is working in parallel, right? We got these two machines working in parallel, right, for this particular job. Okay? And I recognize exactly what that is, and it's something that actually it's something I teach in electricity. So if you have resistors in parallel, it turns out to be the same math, right? But it's very similar to this here. All right, we've got one guy can paint a fence in so many hours, his friend can paint a fence in a different number of hours. They're going to team up together. How long does it take? Right? You say one over the total time is one over the first guy's time plus one over another guy's time. Right? Now there's a whole proof that leads to this. Again, I'm going to skip past that just to jump to. It looks like the book jumps straight to this. Right? But we can take advantage of this. We can rearrange this a little bit for the planters. Now we know the total time of them working together, and we know the time of one of them individually, so we can solve the other one individually. And that's the setup that they're going with. So let's do that. Let's do a book here. Okay. So we know that together, well, I'll say time together, a little subscript there, is 10 hours. Okay. I know the time for one planter alone, I'll call it planter A. How about that? I don't think the 24 rows or 16 rows really matters, do you think? Okay. Would be 6 hours. Okay. So what's the time B equals what? Right, that's basically the setup there. Okay. Now, before I go plug in and check in, I want you guys to see that we can sort of frame the answer and get a basic idea. Right? Because what if these two planters worked at the same rate? Well, if they did, and one worked, hold on. This cannot be the case. Takes 10 hours to plant a field, 6 hours. Sorry. Wait, I got these numbers backwards. Okay. Sorry, this is 6 together and 10 alone. All right, there you go. That makes more sense. Okay. So if you're working by yourself, it takes maybe a 10-hour job. Right, it's an hour job. Right. Now, if you work with someone that worked equally as fast as you, this would have to be 5 hours. The fact that it's 6 hours takes longer, I think this other one is not working quite as fast. Okay, so I'm going to guess that the time alone for this other one is like more than 10 hours, but we're going to find out. So 1 over the total, which is 6, is 1 over the first guy, which is 10, right, plus 1 over x, we'll call it, or let's say time b, because that's what we're solving for, time b. Right, so we did. Okay. So common denominator here. Well, I think these both go into 30, so let's give them up to 30. So this would be 5 over 5, this would be 3 over 3, and then, okay, let's do 30 over 30 for this guy. Okay, and then, I don't know, like this. Let's drop that. Forget that. Okay. Well, I can think of an easier way to do this. Okay. Okay, so we got 5 over 30 equals 3 over 30. All right. Plus 1 over time b. Okay. So I'm going to subtract this equation, this fraction over. So it's 2 over 30 equals 1 over TB. Okay. Therefore, here we go. That was a lot faster. TB equals 30 over 2 hours. Okay. Which simplifies to 15 hours. Okay. Now, this one, your book did solve. Sometimes the examples, they leave blanks, and sometimes they solve it. But they're saying 15. That's in 15 hours. So that's exactly the answer. All right. Okay. Let's do a couple of puzzles here in the book. Okay, let's do one. Let's start number 1. Okay. Solve each equation. Check solution. We got 2x plus 3 over x plus 1. And this is all equal to 3 over 2. Right. Well, each of these denominator guys needs the other guy's denominator. Or we could cross multiply. You know what? We could do that too. That would actually be faster. You know what? I think I'm going to save the common denominator for the next one. Okay. Okay. Look for a little shortcut. Sometimes you can do something like this. You cross multiply. Let's do that. Okay. So 2 times 2x plus 3 equals 3 times x plus 1. Okay. Distribute this 2, distribute this 3. So 4x plus 6 equals 3x plus 3. All right, subtract 3x minus 3x, subtract 6, subtract 6. So this is a single x equals, this is -3, and that's the answer. X equals -3. Boom. Okay. Double check, make sure at the beginning we wouldn't be dividing by 0. Yeah, that's all good. Okay. I'm kind of curious to plug this in. Let's do 2 times -3 plus 3 in parentheses. I'm just plugging the final answer in for x. Divide by, open parentheses, -3 plus 1. Okay. Should be 1.5. It is. It is 1.5. So it worked. Should check. Okay. All right, let's do another one here. Okay, so I'm doing number 7 from the book. It says x over 2x minus 1. All right, now I'll leave a space so I can get common denominator. Let's do 3 over x plus 4. All right, again, space. Whole thing is 21 over. Okay. Okay. It says 2x squared plus 7x minus 4. Right. Now, keeping in mind, you might be setting these up for common denominator, cancel things out. I do see 2x here and an x here. So I already highly suspect that this factors into these two. But let's see if that's actually true. X over 2x minus 1 plus 3 over x plus 4. All right, equals. All right, so I got 21 here. Let's see, does this factor exactly like these? So I definitely need a 2x and an x. Now, if this is 4. Yeah, it sure does. -1 plus 4. Right. Let's watch this FOIL check. 2x, x, 2x squared. Bing. There's 8x minus x is 7x. Bing. -1 times 4 is -4. Bing. It's all there. That's it. All right, so now over here, let's get common denominator. Let's go x plus 4, x plus 4. Okay, so again, we're multiplying by 1. Then over here, same idea. 2x minus 1 over 2x minus 1. Again, this fraction is equal to 1, so we're just multiplying by 1. You're allowed to do that. Okay, now I'm going to distribute this x, distribute this 3, okay, and see where this goes. So I got x squared plus 4x. Then over here I have 6x minus 3. This is all over the denominator. 2x minus 1, x plus 4. And that equals over here 21 over 2x minus 1, x plus 4. Okay. All right, so what you've seen a few times already in this video is the fractions are equal, the denominators are equal, therefore the numerators must be equal. Okay. Now, keep it in the back of my mind, x is not allowed to equal -4 because that would be divided by 0 here. X is also not allowed to equal +1/2 because that would make this 0 and you would be dividing by 0. So just in case I get answers at the end that look like those, because wait, careful, those are extraneous. Okay? But otherwise, I can just take the numerators and keep solving this. So let's go x squared plus, 4x and 6x, that makes 10x. Well, here, I'll do it next step. Okay. -3, I'll subtract over 21 and get the set equal to 0. It's looking pretty quadratic, so head towards that. X squared plus 10x. And then that's -24 equals 0. Oh, yeah. I'm pretty sure this is factorable. Because what would it be? 12 and 2, I think? No. Let's go. Shoot, what is that? 12. Oh, it is 12 and 2. Right, watch this. It's x plus 12 and x minus 2. That's what it is. Okay, let's watch this. X squared. Bing. -2x and 12x is 10x. Bing. 12 times -2 is -4. Bing. It's all there. Therefore, x equals -12 from here, or +2 from here, because each of those would zero it out. Okay. And it turns out neither of those are what I was trying to avoid. Okay. So no extraneous solutions.